My name is Senko Sinclair. I'm the member of the Johannesburg branch committee. I also welcome the chair and also the SIAM team who made sure that we are able to have this presentation today. And furthermore, I would like to thank our speaker for his willingness to talk to us about his work. With that said, I would like to introduce our speaker, Mr. Pathy Muke, who holds a master's degree in mining engineering from Wits University, and also holds a BSc honors degree in mining from University of Lubumbashi in DRC. Pathy is currently pursuing his PhD studies in mine planning and optimization at Wits University School of Mining. Pathy is a junior lecturer at Institute Superior des Techniques Appliquées in Easter Kolwezi in DRC. He is a member of the National Order of Civil Engineering of Congo. His research interests are in mine production, scheduling, and optimization. And also his interests also expand to applied operations research. So without further ado, I would like you to welcome Pathy, and over to you, Pathy, to take us through your work titled A Genetic Algorithm Model for Optimizing Long-Term Open Pit Mine Production Scheduling. Thank you. Over to you, Pathy.
Thank you very much, Mr. Sear, for the introduction. I would like to share my screen with you. Please let me know if you can all see my screen.
Yes, we can see your screen, and yes, it is on presentation mode. Thank you.
Thank you very much. Good afternoon, good evening, or good morning to everyone, depending on the time you are streaming live with us. Thank you for coming to my presentation. My name is Pathy Muke, and I'll be discussing with you for the next 1 hour around the topic, a genetic algorithm model for optimizing long-term open pit mine production scheduling. This presentation derives from a conference paper published and presented at the APCOM 2021 conference. And it is part of the work conducted by myself in partial fulfillment for the requirements of the master's degree at the University of the Witwatersrand, Johannesburg. I would like to take this opportunity to acknowledge the co-authors of this paper, namely Mr. Sihe Leko and Professor Gadbert Musingwini, to whom I'm so grateful for the advice and also this scientific guidance. And also, I wanted to thank the Southern African Institute of Mining and Metallurgy for the invitation and allowing me to come up and present the topic, which is a genetic algorithm model for optimizing long-term open pit mine production scheduling. Without further ado, spend of time, so I will walk you through the presentation, or the content of the presentation is I will introduce the outline. I'll introduce the focus of the study that I conducted. Then I'll walk you through the formulation of the open pit mine production scheduling problem. And then I'll describe the genetic algorithm model and show how I came up with a model that can solve the open pit mine production scheduling. Then I will implement the model that I proposed on 2 block models that were downloaded from the online database MineLib, and then I'll come up with the conclusion. So let's now start with the introduction. Open pit mine planning includes the determination of a long-term open pit mine production scheduling, which is the most important optimization task along the planning process. It is a three-dimensional block extraction sequence that seeks to maximize the net present value of future cash flows while complying with planning constraints. Mine production scheduling problem is computationally complex. Why? Because it involves the analysis of large data sets and requires methods of searching through a large space of feasible solutions, which can be in the order of several thousand of solutions because of the various permutation of block extraction sequence within the ultimate pit limit configuration. Solving the production scheduling problem, therefore, aims to define the best time at which each block within the ultimate pit limit, whether ore or waste block, must be mined and processed in order to guarantee the highest NPV. The problem has been solved by other authors or researchers using different techniques, including deterministic, heuristic, and metaheuristic method. Because of deterministic methods involve variables that are only dependent on the initial condition of the parameters, these methods tend to provide a unique solution, which is very unrealistic for the solving of the production scheduling problem. It was therefore necessary for me to improve the solution approach using stochastic methods that account for certain variabilities and uncertainties. And among these stochastic methods, we have the genetic algorithm. The genetic algorithm is just one of the tools for intelligent searching through a large space of possible solutions. It is a metaheuristic search and optimization approach based on Darwin's theory of natural evolution and the survival of the fittest theory. The idea of the genetic algorithm is that evolution will find an optimal solution for the problem after a number of successive generations, similar to natural selection. And this way of doing things, it's very suitable for solving complex problems, such as the open pit mine production scheduling problem. So why did I choose the genetic algorithm as a method to solve the production scheduling? I'm going to highlight some of the reasons. First, the process of evolution is known to be successful, robust method through the adaptation of biological procedure. The genetic algorithm has proved to be more flexible and demonstrate a strong mechanism to incorporate constraints and uncertainties in the solution procedure. Again, the use of crossover and mutation genetic operators are suitable for exploiting and exploring a vast space of feasible solutions. The solution represents, in the form of a chromosome, matches with the block model structure in the open pit mine. And this genetic algorithm has as well a huge potentiality to optimize at the same time the open pit mine production and scheduling, as well as the pit limit configuration. So let's now formulate the production scheduling problem with mathematical expression. So we're going to, first of all, formulate the objective function with the aim to maximize the net present value of future cash flows of the mine by, of course, providing the best extraction sequence of blocks from the pit. So we're gonna use linear programming to formulate this problem, maximizing the function Z, which is the double summation of the discounted economic value, V, realized by mining and processing block I during period T. XIT represent the proportion of of block I extracted during POT. So therefore, the purpose of this study was to develop a meta-heuristic approach based on the genetic algorithm to solve the production scheduling on a long-term plan in a three-dimensional space in order to determine the best time at which each block within the pit should be extracted to guarantee the maximum value of its content. So solving the production scheduling on a long-term plan takes therefore into consideration some technical and operational constraints, which include mining and processing capacities, ore grade control, pit slope angle, and the mineral reserve constraint. Talking of the mining capacity, this represents the total tonnage of material that needs to be mined or extracted during each period of extraction. And this mining capacity is determined from the size of the equipment used, as well as the size of the mineral deposit. So mathematically, this constrains the objective function of the production scheduling by defining the minimum and the maximum mining capacities that need to be extracted in every year of extraction. And then we have the processing capacity constraint that defines the total ore material to be sent to the plant. And it's defined as the input capacity to the plant and constraining the objective function of the production scheduling by defining the minimum and maximum processing capacity to be sent to the plant. And we have another constraint, which is the pit slope angle that represents here the block predecessor's constraint and ensure that the geotechnical stability of the pit is observed. So before, for example, mining the block X here, all the overlying blocks should be removed a priori. And these blocks are defined within the overall slope angle that is a constraint in optimizing the production scheduling problem. And mathematically can also be expressed in order to constrain the objective function that we are trying to optimize. We've got as well the ore grade control, which is also an important constraint that defines the quality of ore material to be mined in every year of production. And finally, we've got the reserve constraint, constraining the production scheduling process by only ensuring that every block within the ultimate pit limit is scheduled only once. Now, having in mind our problem described and formulated using mathematical expressions, then we now want to use this method, this technique, which is the genetic algorithm, to solve the problem. The genetic algorithm is essentially run in 5 broad steps. Step 1, which is creating a random initial population of chromosomes, which is a set of potential solutions for the problem. Step 2, evaluate the fitness value, which measures the quality of each potential solution presented in the form of chromosome. Then the reproduction process by breeding pairs of parent chromosome. Step 3 of the process consists of generating a new population of solutions by applying genetic operator selection, crossover, and mutation to prevent the process from getting stuck at a local optimal solution. And step 4, here then we're going to replace the least fit solutions with the improved solutions. So the chromosomes that are more fit have a better chance for survival. So here we are going to observe the survival of the fittest theory. And finally, step 5, on which we're trying to improve in the fitness value of chromosomes in the population. And if there's no improvement, then the algorithm will send back to step 3 to generate a new population and go back to step 4 to place the least fit until we reach the termination condition whereby there is no room of improvement for any chromosomes or list of blocks. So on the right-hand side of the screen, I've created the flow charts of the genetic algorithm in parallel of the 5 steps of the genetic algorithm procedure. So we start up with the input block model as the search space, and then we generate randomly the initial population of feasible set of blocks from the search space. Then we compute or calculate the fitness of each potential solutions from the initial population. And then we create this loop to apply the genetic operators, genetic operators in order to improve the solution over generations. And then now, it is important to understand how the genetic operators therefore worked during the implementation of the algorithm. Why we need to adapt how it works with the problem that we are trying to solve. So therefore, I wanted to define some of the concepts of the genetic algorithm as it is applied for solving the production scheduling problem. So the search space for me represents the ultimate pit limit configuration that represents the contour of the pit that yields or provides or deliver the maximum value of the mineral deposit. The initial population in the production scheduling optimization comprises of a set of randomly generated feasible solutions. And the chromosome is similar to a list of mining blocks whose economic value must be improved through the application of genetic operators. And each block in the list represents the gene and is assigned a block number for identification in the chromosome. We've got the fitness function that represents the objective function, of course, that determines the economic value or the fitness of the chromosome. The selection governs the likelihood of a chromosome to be selected for reproduction based on its fitness value and the quality of all blocks. The crossover operator improves the fitness value of the parent chromosome by reproducing 2 new offspring chromosomes. And finally, the mutation here improves the quality of the offspring chromosomes by changing or altering some of the genes within the chromosome to comply with the mining and processing capacity constraint. So after creating the flow chart of the proposed genetic algorithm, I then developed a pseudocode, which is an important key principle of an algorithm, by sketching out the structure of the program before the actual coding takes place. So this pseudocode starts off input of the parameters, including the search space, the size of the initial population, the maximum and the minimum mining capacities, as well as the maximum and minimum processing capacities. And then we open up a loop in which we're going to generate randomly the initial population of feasible solutions with respect of the block predecessors constraint. as well as the mining capacities. Then in the second loop, in which we then going to implement the genetic algorithm operators, which is the mutation, crossover, and the selection, as well as calculating the economic value or the fitness of each chromosome. And after that, we come up with the termination conditions, which is only met when there is no room for improvement for any chromosome in the final population. So on the right-hand side, I am illustrating the proposed GA-based model, which was coded and written in Python environment. So this is just a couple of the lines of the code that, that we wrote in order to implement or run the model on a block model. So as case studies, 2 mining instances were used to test the proposed GA-based model, which was developed in Python environment. And these mining instances were downloaded from the online database site, MineLib. Newman 1 and Zerk small mining instances are basically academic open pit mining data sets that are very, very convenient for testing open pit mine planning and optimization related problems. The Newman 1 model contains 1,060 blocks, while the Zerk small contains 9,400 blocks. Their respective descriptions include the number of blocks, including the ultimate pit, the maximum immediate block processors per block. It was also given the discount rate, the minimum and maximum annual mining capacities, as well as the minimum and maximum annual processing capacities for each mining instance. So this is now the representation of how the 2 block models are represented in 3-dimensional space. So on the left-hand side, the Newman 1 model containing only 1,060 blocks, which is very small. And here, all the blocks are represented, are located according to the center coordinates of each block. And on the right-hand side, the Zerk small model containing 9,400 blocks. So now the problem here is to run the genetic algorithm model over these blocks in order to generate the sequence of extractions of these blocks until the depletion of all of the mineral reserves. So before using the genetic algorithm, it is required some of the input data. And these data are obtained from the ultimate pit limit data set. And it includes, of course, a description file for the block model containing information such as the block ID, the block spatial location, ore grade, block tonnage, and block economic value. And a file that contains the direct block predecessors for each block in the model called the block precedence file. And of course, the definition of the minimum, maximum mining capacities constraining the amount of material to be mined per period. And the definition of minimum and maximum processing capacities for the quality of ore to be supplied to the processing plant. And finally, the definition of the duration of each extraction period. Here, it is expressed in years. So now, when applied the genetic algorithm on the Newman 1 ultimate pit block model, the proposed genetic algorithm-based model delivered a 4-year extraction plan for the depletion of the mineral reserves with an NPV of nearly $22 million. And a 3D production layout is displaying here, from which 350 blocks are scheduled for extraction in year 1 of mining operation, 350 blocks in year 2, 308 blocks in year 3, and 52 blocks in year 4. So this is a very small block model, and it was needed to test our genetic algorithm model that was developed. And the graphic shows all the blocks that need to be mined in the first year of production, in blue, in red in the second year, and in black in the third year of production. And when it was applied on the exact small block model, the proposed GA-based model delivered a 17-year extraction plan until the depletion of the mineral reserves with an NPV of about $800 million. An illustration of the production layout is displayed only for period of extraction of 13, 14, and 15, of which the number of blocks scheduled 538 blocks, 525 blocks, and 521 blocks, respectively. So it shows the sequence of block extractions over the life of mine. So in order to validate the solution that were obtained by applying the proposed GA model, a numerical comparison was conducted against the total sort algorithm, which is the best known solution for the problem, and was provided on MineLib at the time of this study. So the two open pit mine production scheduling long-term plans generated using the proposed GA model for the two case studies delivered NPVs which were different of 7% and 8.3% respectively when compared to the best non-optimal feasible solutions obtained using TopoSort approach, of course recorded on the MineLib database. And the running time of the genetic-based model for the Newman one and the small mining instances was about only 14.28 seconds and 17 minutes for the small mining instance. Therefore, for our further comparison, and since the NPVs were generated over different extraction periods for each mining instance, it was therefore necessary to perform an equivalent annual NPV analysis. And this analysis shows that the GA-based model produced a better equivalent annual NPV of $6.6 million compared to $5.1 million from the TopoSort solution, the Newman one mining instance. And for the ZAC small mining instance, the GA-based model generated a slightly lower equivalent annual NPV of $99.8 million compared to $102.5 million. So as a conclusion, we've discovered that the genetic algorithm-based model can be solved to optimize the open pit mine production scheduling problem in three-dimensional space. And the best solution is generated through a process of searching and improvement from a set of multiple feasible solutions in the search space. The crossover and mutation genetic operators are very suitable to exploit and explore the large space of feasible solutions. And the solution representation as a chromosome matches very well with the block model structure in the open pit mine. The result, therefore, showed that the genetic algorithm-based model produced comparable solutions against the best known solution at the time of the study, and thus indicates strong potential application of the genetic algorithm-based model to solve open pit mine production scheduling problem in the mine planning process. So this comes to the end of my presentation. Thank you again for your attention. And if you have any question, please do not hesitate to ask, and I will answer to the best of my knowledge. Thank you once again.
Thank you very much, Pathy. I think we can open the floor for questions. Gia, please assist me in terms of, I don't know if the audience is unmuted so they can be able to ask questions. On the Q&A tab, I haven't seen any question. Therefore, I assume that the audience, if they have questions or comments, they can then be able to just unmute themselves and speak. Pathy, the question that I see now is the genetic algorithm, how does it compare to a discrete event simulation model?
Can you please repeat that, the second part?
How does the genetic algorithm compare to a discrete event simulation model?
Well, I did not try. I think they are very different. I did not investigate on that one to find out how the genetic algorithm compares with the simulation model. It does not simulate any model, but it's only try to find the a solution based on something that was generated before and to improve it. So I didn't compare with any simulation technique.
Okay, thank you. The next question from, the previous question was from Hydra Dreyer. The next question is from Mark Buntin. The question is, you mentioned that the benefit of using the GA-based model is speed. How does it compare to the TOPOSOT model in terms of speed?
Well, I found out that using the genetic algorithm, we can solve a small block model in a very short period of time, as it was experimented by myself on the Newman one method. Instance, we only we were able to find the best solution only after 14.28 seconds, which is very, very fast. Unfortunately, the running time of the TOPOSOT algorithm were not given by the people who developed that technique. But for on the Zaxmol mining instance, the genetic algorithm ran for 17 minutes to come up with the best extraction sequence. So this is as well a very short period of time as compared to the size of the block model containing 9,400 blocks. So again, the running time of the TOPOSOT algorithm on the Zaxmol mining instance was not given. And I might assume that it would have taken more than 17 minutes considering the size of the Zaxmol mining instance.
Okay, so maybe just to it's a follow-up from Mark as well. So I think maybe if do you have an understanding of the type of algorithm TOPOSOT is based on? You mentioned deterministic, you mentioned heuristic, and meta-heuristic. I think that you then be able to gauge in terms of time? Because Marcus' question, as we've answered correctly, is along the lines of now applying these algorithms on a large block model. How then does it fare in terms of time? Maybe if you look at the, I don't know if the Mindleap did mention the type of algorithm Toposot is based on in terms of deterministic, heuristic, or meta-heuristic.
Okay. I've done some research. This Toposot algorithm is one of the meta-heuristic approach because it combines the natural behavior of some specific species and also mathematical expressions. So yeah, it's both. It's meta-heuristic approach.
Okay, thank you. And Sinisa Vuko is asking that could you model changing price or cost of excavating a block over time using the genetic model algorithm?
I think it can be possible using the genetic algorithm just to to understand how the cost changes over time. Maybe we can build up a model based on the concept of the genetic algorithm to determine costs of production in each period of extraction. I think this can be done, but it will require a thorough analysis of the cost and as well as how the genetic algorithm works and how can be adapted to this particular problem.
Okay. I'm going to go to see other two questions here. So I think just to add on that, on your response, Sinisa, is that you will then most likely have to model it in two ways. The first part is Pathy saying that it means you will use the genetic algorithm to just model the price and cost, and then it will feed onto another genetic algorithm who's doing the scheduling. Then there will be in communication, whether it's a linear or lateral communication, to then depend on what is the most important constraint. The next question is from Hydra, and I think it's building on the previous, no, it's not building. The question is, does the genetic algorithm generate a block plan or a new schedule to be used as an output? So the output that it produces, does it give you a block plan or a new schedule to say, now, this is a sequence of your extraction, start with this block, go to this block, and so on, in maximizing the value?
Okay, the genetic algorithm delivers a new plan. It depends on the time frame that you doing your scheduling. For example, for my case, I did the scheduling over the long-term plan. So I guess that you can as well break it down to the medium and as well as to the short-term plan. So it, of course, start up with the initial solution that were randomly generated. So if you, that's why this is also a stochastic. So it does not give the very, very optimal solution because of the randomness involved in the procedure. So it only gives a near optimal solutions, and it adds to the decision that needs to be made when doing your production scheduling. So it gives the product a sequence of extraction, but it's not. It doesn't give the what's called the blank block of extraction. So I think it can only do the sequence of extractions of block.
So maybe just a follow-up. When you're saying it gives you the sequence of extraction, as a man planner, is one able to see based on the periods of extraction, which block to mine when. Whereas if you're using a year as your measure, say this year mine these blocks, am I able to identify those blocks to mine in year 1, year 2, year 3, and so on?
Yes, yes, of course. The algorithm, the way the algorithm runs, it can go through the block model to find which block is fit to mine in every year of production, depending on the quality. Because the conception and on which also I was based for when developing the model is to first of all look for those blocks that have high grade content to be extracted in the very first years of production in order to reduce the payback period to the capital cost. So it's really focusing on the blocks that contains high value, and then move to those contains less and less until to the waste blocks. So the focusing is mainly on the blocks that contain high grade.
Okay, thank you for that. Alexander Mayer is asking, how many viable solutions do you get from a single run? And then, okay, go ahead.
Yeah, thank you for that question. And this is a very important question. So the idea is to run the model that will generate different generations, different populations. For the new main one, I came up with the optimal solutions after running 4 to 5 generations of different populations. So I started with the initial population, the model ran over it, improved it, and then went back again, apply the genetic operators once again, the mutation crossover, and as well as the selection. So in the way the genetic algorithm runs, remember we based on the survival of the fittest. The first, after the first generation, the model will only select the fittest solutions that contains the highest value. Let's say the half of the population, and then breed those fittest solutions in between them, and then those breeding will then generate children or offspring in the next generation. And then coming to that generation, then we apply again the genetic operators to improve those offsprings by reproducing new other offspring, which are better than the previous. Which are better than their parents, and so on and so on. So the new main one model, I got the solution, the best solution after 5 generations. But for the Zaxmol mining instance, the best solution came up only running after 3 generations of populations.
Okay. So in terms of now, this is just a follow-up on the same question from Alexander as well. Is now as you are doing your the evolution over time, are you able as an output to get also the previous generation solutions, or you only get the final best solution?
The algorithm considers well the previous solutions, but it makes sure that those previous solutions are improved over time. So if there is no improvement, the algorithm will reject those solutions and select the other best solutions to be involved in the next reproduction.
Okay, thank you. And since is asking this, and thanks for the previous question. And it's asking, is it possible, or could you make a wrapper, or in terms of the block selection, that says calls for the first 200 blocks at each instance, and it uses those 200 blocks as an input for the next 200 blocks, while separately introducing a list of changes that will take place in every 200 blocks. This changes the math conditions programmatically, not the GA itself. So you call blocks, maybe let's say you select the first 200, or you call the first 200, which of course will then will be used, or whatever solution that it produces will be used as an input for the next 200 blocks in a block model, looking at the block model, while separately introducing a list of changes. It means somehow you are modifying your constraints for every other 200 blocks. So we're not changing the code, but now you're just modifying the constraints based on the output of each 200 blocks selected per period or per run.
Okay, I don't know if I understand the question very well, but I'll try to answer to that question. What happened is the first run on the block model, the algorithm will select the best blocks that need to be mined, let's say in the first year of production.
Okay, but maybe sorry, before you proceed, I think maybe the question, based on what you just said, I think the question then is asking that let's say you have a block model of 10,000 blocks. Are you able to select some blocks, not the whole block model, select a number of blocks to start your optimization, which will then feed into the next 200? And as you are feeding into the next 200, be able to modify your constraints as you proceed.
Yeah,
if
true.
I'm getting the question correct, yeah.
Yeah, true. It is possible. It is possible to do that. To constrain the algorithm, only consider a certain number of blocks. Okay, let's say as the ultimate bit configurations is represented, we can constrain the algorithm to let's say select blocks only up to level 5 of the pit that need to be extracted for the first year, second year, and whatever. And the rest of the blocks should be considered in the following of where you'll be left off. So yeah, it is possible, and also it is possible as the pit deepens, you can also change some constraints in order to be realistic on what you are doing in terms of scheduling.
Okay, thank you. I think that question, Sinis, I think in a nutshell, it means it is possible as the user, you can be able and to make those modifications. And then Mark is asking if you have any plans to commercialize this algorithm.
Well, thank you for that question. Okay, this is an experiment, a study that I did, and my idea was to maybe create an add-in of this algorithm on the already existing software that we use for production scheduling, like the Mineshed. So we can do some of the part of the coding to add this model to the existing software to improve as well the way the production scheduling is done on a software. So far, I'm still working on it. Maybe at the end in the future, I'll find a way to add in or incorporate it into another software just to improve how the production scheduling is done.
Oh, okay. Now, maybe my question this side is, unless I missed it in your presentation, is you spoke about, I think the first mine, I think it's Newman model, is around about 1,000 blocks, 1,060, and the other one is 9,400 blocks. But then the dimension of the blocks, I think, will play a huge role in understanding how big or how small the model is. If it's 1,060 blocks, but we may find that the block size is around about 20 by 20 by 20, which is large. So I understand in terms of the block sizes and estimated if you don't remember the exact values.
I think we understand that the production scheduling is a very complex problem depending on the size of the block model. So we can see for a small block model, the algorithm can run very fast to come up with a solution. As I did it in only 14.28 seconds to solve the Newman 1 model, which contains only 1,060 blocks. But the bigger is the block model, the longer it's gonna take to run the model and to schedule the extraction sequence of the blocks. So I think it's gonna be exponential trend, because I can see just from 1,060 blocks, the model could be run only for 14 seconds, but a model of 9,400 blocks, 17 minutes. So I did not try it on a very big block model. Maybe I'll investigate that in the future to see how the trend in terms of running time is compared to the size of the block model.
Oh, okay, thank you. Maybe I think for me, one last question. I don't see any questions as that. So let me say maybe one last question. Out of the constraints that you considered for the NPV calculation, what other constraints can one add? I mean, I note the capacity, mining, processing, slope, and I forgot the fourth one. What other constraints one typically would consider in an open pit environment?
This is one also an important question. Thank you for that. For the sake of simplification of the problem, I only considered those 5 constraints: the mining capacity, processing capacity, pit slope angle, the ore grade constraints, as well as the reserve constraint. This is for long-term plan. We can consider other constraints when we break it down to the medium and the short-term plan, because we're not going to include more operational constraints, like the position of the excavator, the position of the truck, and the opening of the bench. So all those constraints, when now we want to deep and cut it down to the medium term and short term plan, more constraints should be also considered.
Okay. Now, thank you very much. I don't know if we have one last question or we are all covered at the moment. And I believe that if there are any further questions, Pathy, you wouldn't mind that SIMM share your contact details, the email address, so that any member who's looking for further discussions can be able to access you and have a discussion with you. I don't know if it's okay. Oh yeah, Sinisa has a question, and then yeah, okay. Sinisa has let's take one last question, and then we can close. Sinisa is asking, the sequence of excavating blocks is only one. So that means there's only one sequence of extraction, but that is because of the constraints. So in the extraction process, the way you extract your blocks, is asking if there's only one sequence, or is that because of it's because of the constraints that you have, because you can see all sequences that are close to the constraints.
Okay. As I was saying, this agentic algorithm can give different sequences, but we're going only to select the best sequence of extraction. That's why we call it as well a decision in making our or choosing the optimal way of extractions. So it gives different possibilities to extract the blocks, but you're gonna select only the best that meets your requirements and the conditions that you set up. So I don't know if I answered to that question.
Okay. No, thank you very much, Pathy. I think okay. A follow-up. Sinisa is asking, what if there are 20 sequences within a $20? This means it's the NPV. I am assuming the value. What then? How then does the algorithm handle that? And also, is the stripping ratio factor considered?
Yes, true. The stripping ratio is considered, and we look for an ascending trend of the stripping ratio as we deepen the pit. The model, this can also be a constraint. This is very, very correct. The stripping ratio can also be also a constraint. I considered, I took into consideration that one when I was writing code, to say that when we're developing the pit or extracting the blocks, we make sure that we tend to have a stripping ratio that's going up. So meaning we start by mining more ore blocks than the waste or the overburden material. So yeah, that also is considered. And the other part, what was that?
It's looking at the value, saying that you have numerous sequences. What if they are within, let's say, a range of $1 in terms of the NPV, the ultimate NPV? They vary around about $20. How does the algorithm handle that? Does it just go straight to the highest NPV, or you can look at the practicalities of extraction and then select maybe another one instead of the one with the highest value, but still close?
Okay, true. For now, what I did in my model, the algorithm goes straight to the highest NPV. But I understand that in a real world case, the mine planner can also have some other constraint that's going to lead the decision in terms of choosing what sequence to develop. For example, you can go for the highest NPV, but it's not realistic, and it cannot be done practically. Then going to choose the one that has less NPV, but practically can be done. So yeah, there's a balance. So for now, for my studies, for what I did, I only considered target the highest NPV.
Okay. No, thank you very much. I think then, as I did request, maybe you can give consent if we can be able to share your email address for those who would like to contact you later.
Yes, I will share my email address.
Okay, thank you. So I'm going to hand over to George Dallas, who will then do the vote of thanks. Thank you very much, Pathy. Over to you, George.
Thank you very much, CK. I've also opened up the video so attendees and panelists can see me. On behalf of the Johannesburg Committee, SIMM Committee, and Donnie Jansen, who's also present, he's our president or chairman of the committee, would like to express our thank you, first of all, to CK for organizing this, and of course to Pathy for a very, very interesting presentation. I come from the metallurgical side of the fence, and I find this, you know, very, very topical, because, as I say, any mining company's only got two assets. One is the pit itself and the management of it and the extraction of it, and this is what Pathy's presentation was all about. And then the next one is obviously people, and that's another subject all on its own. So I'd like to thank both Sika and Pathy for today's presentations, and they're putting it together, all the preparations. I'll also like, as we always do, especially in these testing times with virtual meetings, to thank the Secretariat, you know, Kia and the team. Thank you very much for that. It was very successful. We had no glitches. And then I'd also like to take this opportunity to communicate to the audience out there that we have been on a virtual setup now for the last 2 years, and I'm happy to say it's coming to an end. We're working hard, and we're looking at the next presentation in April, all going well, to go back into a sort of physical contact situation at our previous venue, Wally. And please look out for the next round of communications that comes out as to the subject choice and also the venue. And we look forward to seeing you all in person sooner rather than later. Thank you very much.
Okay, thank you. I think I'll hand over to Kia, and on my side, thank you very much, and have a good evening. Over to you, Kia.
Thank you, Sihe. Good night, everyone.
Okay, no, cheers, everyone.